So now we're going to talk about what are the effects of angiotensin II on the system. So just a quick review of how we got here. We said that the RAS system, the goal is to essentially respond to a couple of stimuli. One of the stimuli is decreased renal perfusion, and the other is a drop in blood pressure. So what does our body do? Our body acts to instigate mechanisms that is going to bring back the homeostasis, bring back these levels to the value that they want to be. If renal perfusion is low, we're going to act to increase that perfusion pressure. And if our blood pressure is low, we're going to act to bring back solute, namely sodium, to increase our overall blood pressure. Remember, sodium is ultimately the thing that drives our volume status. Water is going to follow sodium by the principle of osmosis. So if we look at this drawing right here, remember osmosis. Which way is water going to go? It's going to go this way, right? It's going to be pulled to the area with more solute. So by bringing in sodium in our body, we're ultimately going to bring in more water, and that's going to increase our volume status overall. So that's the general goal of the RAS system, is to respond to these low levels, bring back sodium so that we can return to our baseline and maintain homeostasis. Now I really want to focus on this molecule right here called angiotensin II. So this molecule right here essentially has several different effects on the body, and it's important to know that they are all working simultaneously with the primary goal of maintaining our pressure volumes, our electrolyte balance, and other important effects to keep our body working in its optimal state. So the first one we're going to talk about here is systemic vasoconstriction. Notice this is saying that AT2 or angiotensin II binds to the AT1 receptor, which is found on vascular cells, and ultimately increases blood pressure. This makes sense because if we vasoconstrict a molecule, if we take a blood vessel that's, say, this size and we constrict it so that it's this size, you can imagine this is going to increase the pressures against the walls because we're effectively narrowing the space that blood is able to go through, versus over here, right, there's more space for blood to go through, so there's less pressure. So by vasoconstricting, we're going to increase our blood pressure. And a similar part of this mechanism, but ultimately something that we need to remember as well because it's super important, is this idea of efferent arterial vasoconstriction. So we already said there's vasoconstriction, systemically, right? But it's important to remember that the efferent arterial is actually constricted to a greater amount than the afferent arterial. Why is this important? Because this is ultimately what allows us to preserve our GFR, or our glomerular filtration rate. Just as a quick refresher, this is our equation for the filtration fraction. It's the GFR divided by the renal plasma flow. And also remember that our afferent arterial is the one entering the glomerulus, and our efferent arterial is the one leaving the glomerulus. And so if we move this equation around a little bit, we're going to get that our GFR equals our filtration fraction times our renal plasma flow. So how does the efferent arterial constricting maintain our GFR? Well, if our renal plasma flow has decreased overall, right? Because remember, this RAS system is activated in settings of low blood volume or low pressures, right? So if we have low pressures and low blood volume, our renal plasma flow, the amount of plasma that's actually getting to the kidneys, is going to be decreased overall. So the system is acting to balance that out. And the only way to balance that out and maintain GFR is to increase how much of it is actually filtered. If we take this efferent arterial and make it more narrow, that is going to increase the pressures in the glomerulus because now there's less of an opportunity for it to escape, right? If we've constricted the vessel that is allowing the fluid to leave, well, now it kind of gets backed up and there's more pressure, and thus it's going to force more of that through the glomerulus. More of it is going to be filtered, and so that's how we increase our filtration fraction, by constricting our efferent arterial. The next important thing to talk about for angiotensin II is aldosterone secretion. So this is typically the first one we learn about as medical students, and certainly one of the primary ones, but it's important to know that there's actually this is a multi-system response. The RAS system affects many different areas to ultimately reach its goal and have a full effect in the body. So this aldosterone secretion occurs at the level of the adrenal cortex, and it's super, super important because aldosterone has many effects on the body. The primary effect of the RAS system is to actually retain our sodium, and so naturally it's going to stimulate receptors that will increase our sodium reabsorption at the expense of our potassium and our hydrogen ions. We talked in our nephron transporters video about the collecting duct and how stimulating the sodium reabsorption ultimately causes an increased excretion of potassium hydrogen ions. So go back and check out that video if you're not familiar with how this process works. But just a quick review and reminder is that it stimulates the sodium potassium pump. So that's going to reabsorb sodium at the expense of secreting potassium. It's also going to stimulate ENaC. Remember, that's the epithelial sodium channel. And it's going to stimulate potassium conductance. So again, the collecting duct video, we talked about this more, but essentially this is going to allow more potassium to be secreted into the nephron and ultimately excreted from the body. And just as a quick refresher, the reason is because there's a lot of potassium in the cell. We have the sodium-potassium transporter, and in the collecting duct, there are essentially channels that potassium can move down its concentration gradient and down its electrochemical gradient. And by stimulating these channels, creating more of them or allowing them to be more active, potassium ultimately will leave the cell and then go into the nephron to be excreted. The next important effect that angiotensin II has is the ADH release. So ADH stands for antidiuretic hormone. It's a hormone that is released from the posterior pituitary, and its primary effect is to reabsorb water. So remember, this H2O reabsorption is done through something called aquaporin channels. So just as a quick refresher from the collecting duct video we did in the nephron transporters section, ADH will bind to a receptor right after it's been secreted from the posterior pituitary. It'll then cause the release of vesicles that will then insert on the apical surface of the cells facing the nephron. This will increase the amount of water channels on the apical surface and ultimately allow more free water, or H2O, to enter into the cell, ultimately entering back into the body. And this is one way that we can essentially increase our volume status by just bringing back water by itself, right? Because typically we're bringing back sodium, and that is going to ultimately bring back water through the principle of osmosis. But here's a scenario where we're actually just bringing back what we call free water, as in it's just water by itself being transported through specific water channels. And the final important thing to talk about here is PCT stimulation. Again, in the nephron transporters chapter, we talked about the proximal convoluted tubule in the kidney, but here the specific ways that this system affects those is that it increases the sodium-hydrogen pump. Ultimately, this leads to increased sodium, water, and bicarb reabsorption. Again, the primary goal of the RAS system, if I had to simplify it into one thing, it's to bring back sodium. It has a lot of other effects. It affects a lot of other areas in the body, but that's the primary goal. Because if we bring back sodium, we're bringing back water. And if we bring back water, we're replenishing our volume status. We're maintaining our blood pressures. We're maintaining our renal plasma flow. And that's really just the overall goal of the system. So if we look at our PCT diagram in the upper corner, we're saying that angiotensin II stimulates this transporter right here, which is ultimately going to bring back more sodium, right, into the body and excrete more hydrogen ions right here. But notice that excreting more hydrogen ions ultimately allows it to bind to more bicarb, which is then reabsorbed by a different transporter, also in the proximal convoluted tubule. So that's how we get an increased amount of reabsorption in water and bicarb, in addition to an increased amount of sodium reabsorption. And this occurs through our enzyme that we needed to know, carbonic anhydrase. So if you're not super familiar with this, go back and watch that video again on the proximal convoluted tubule to understand this process, because again, here we're just building on it and saying we're stimulating the receptor, so we're going to have more of this occurring. So the main thing I want you to take away from this video is that the RAS system acts to increase our blood pressure. It also increases our perfusion pressure to the kidneys. The primary way it does this is by increasing reabsorption of sodium, but there are several different mechanisms in which this goal can be accomplished, right? We've talked about all of them here. These are all very important mechanisms to understand and make up a really important concept in renal physiology.